calculus conceit. A differentiable function, looking at its graph, when you zoom in, it looks like a line. We'll just call those smooth functions always. Linearization of a function. A recap of everything we've done. I'm starting at some point, say 3. Fill in the height and fill in the slope. The height is the function value. The slope, the derivative value. Now that I have a point and a slope, I can make a line. This line is approximating the graph of the function. So it's our tangent line to the function at 3. Grab some point on that line that'll approximate our function values. Calculate our differentials. Differentials always start at the point we know. And then rise over run is our slope. It's the differentials at x equals 3. And we have two different notations, and they mean the same thing. Write down what the differential is, head minus tail, head minus tail, and fill in our slope. df over dx is our slope. And then we just solve for y. That function of x outputs a y value. That function is called the linearization of f at 3. It's the function that generates the tangent line. Let's do an example to put in some numbers. How about arctangent? So we'll look at the principal branch of arctangent, inverse tangent. We computed its derivative already. We know what it is. So in our schematic, our function value, and then below it, we put in our derivative function. So given an x, we output the height, inverse tangent. We output the slope, 1 over 1 plus x squared. So now let's do an example. I want to find the linearization of arctangent, inverse tangent, at x equals square root 3, one of my known values. Right, there's only 3 known values. Inverse tangent of square root 3 is one of them. Set up our drawing. So at the point square root 3, inverse tangent square root 3, it's pi over 3, slope, plug in square root 3 into the derivative, 1/4. Set up our tangent line, grab a point on it. It has an xy coordinate. The y coordinate is approximating the inverse tangent. Set up our differentials, going from the point we know to the point we don't. Rise over run is slope, and solve for dy. So there's our changes. A change in x, 1/4 of that gives the change in y. Write down what our differentials are in terms of points. Head minus tail is our differential. Solve for y. And there's our linearization. Now we'll use this to do an approximation. Use a point we know to approximate a point we don't. So we're at square root 3. Let's use this to approximate inverse tangent at 2. That's pretty close. Square root of 3 is 1.7. Using linearization, using our tangent line approximation, same thing. Grab our point. Now the x-coordinate's 2, so the y-coordinate is approximating inverse tangent of 2. Set up our differentials. Differentials are at square root of 3. Solve for dy and plug in. Solving for inverse tangent 2. There's our approximation. If I just want to do algebra, I have to remember the formula, so I redo the construction just in general. Instead of 3, use x naught and generate the formula. And then I just plug in for every problem. Function, inverse tangent, its derivative, 1 over 1 plus the square function. X is 2, x naught is root 3.